The goal of integration using U-Substitution is to take an integral that is complicated and turn it into an integral that is not so complicated. So right here we have the integral of sine of 3x dx. Now, I know I can solve the integral of sine of x, and so my goal is somehow to turn this integral into something that is easier to solve. Well, the complicated part is that 3x. So I'm going to take that 3x and set it equal to the variable u. And then I'm going to take the derivative of u. So the derivative of 3x is just 3dx. I now try to see if I can somehow turn my original integral to write it in terms of u. So I have that 3x inside, that's an easy substitution, but I need to end with a 3 times dx, and I just have a dx there. Well, if I just rewrite this now as a sine of 3x, and I want to put that 3 dx out here, I've changed my original integral. But since that 3 is a constant, if I put a 1/3 out in front of the integral, I now have the same exact integral that was stated before. Now I can directly substitute my u's and my du's into this new adapted integral. So if I rewrite it as such, as 1/3 the integral sine of u du, this 3dx being that du, I now have an integral in terms of a different variable that is much easier to solve. So the 1/3 stays out here, and the integral of sine of u is just negative cosine u, and we have a plus c, and that constant. Well, now the negative sign comes out here. I have a negative 1/3 cosine u plus c, but my original equation started with 3x. And so, but u equals 3x, and now I can substitute that u back in for this u, and I'm left with a negative 1/3 cosine of 3x plus c. Now that was an easier integral. Let's see if I can get one that's a little more complicated. What if I want to find the integral of 5x over 4 plus x squared dx? So there's many different u's you could try and see if it ended up working out. I usually try to take the more complicated part, but not super complicated because there's that squared there. But I'm going to set my u to just be that 4 plus x squared. So then if I took the derivative of u, du, derivative of this side would just be, well, 2x dx. Well, I see I can directly sub in that u for this 4 plus x squared, but the 2x and 5x don't match up. Well, I know I want to have a 2x dx up top here. And then if I have a 4 plus x squared, I now can substitute that u in for here and then du for the numerator. But there's that 5. Well, the 5 is just a constant, and if I had pulled it out here, it's still the same equation. The 5 comes out here, the 5 comes out here. It really hasn't changed it. And so now I just need to deal with that 2. And I can do so by just, oh, that's a 3. Putting it in the denominator. And now we have 5/2 times the integral of 2x dx over 4 plus x squared all squared. So now I have it in terms of u and du, and this becomes an integral that's much simpler to solve, which is just du now on the numerator, and then u squared in the denominator. Now I don't like dealing with u squared in the denominator, and I like to turn it into a negative exponent. And so if we have 5/2 here, the integral of u to the negative 2 du, I now can solve it by leaving that 5/2 out front. And then Well, the integral of u to the negative 2 power is just a negative u to the negative 1 plus c. I now can rewrite this 5/2 with the negative out front here times, well, u is in the denominator plus c. And now I can plug those back in, those u values, to get a negative 5 over 2 times my u value, which is 4 plus x squared. And don't forget our little plus c. And so our integral here now would be negative 5 over 2 times 4 plus x squared plus c. And of course you could simplify that out and distribute that 2 to both parts, but you now have the integral of your original function. We could test this to see if that it is the right integral by taking the derivative of this function here, which would give us that 5x over 4 plus x squared all squared. Thank you for watching and have a nice day.